In this chapter, we're going to focus on the chemistry of gases. In some of the preceding chapters, we've looked at the chemical properties of different substances. We've also studied the kinds of forces, or chemical bonds, that hold together ionic substances and molecules. It is the nature of chemical bonds that actually dictates their chemical properties. In this chapter, we'll actually start to look at physical properties of materials. We'll start with gases, and then in the next chapter, we'll look at the physical properties of liquids and solids. We start studying gases first because they are the easiest to understand. Their behavior will help us explain some of the properties of liquids and solids in the following chapter. Let's start out by just looking at some of the basics of gases. Gases are composed of widely spaced molecules that are in constant motion. Gases completely fill any container into which they are placed, meaning they have no definite shape or no definite volume. Gases exert a pressure when they collide with the walls of the container. Notice the image on the right. The gas particles are bouncing around inside of the fixed container, hitting the walls. The more that the particles collide with the walls, the greater the pressure that the gases will exert. Gases have low densities. Densities are typically measured in units of grams per liter. Gases can be compressed down, meaning we can shrink them into a smaller volume. And gases will mix freely and quickly with one another. These are just some of the things that we'll explore throughout this chapter. Gases exert a pressure, and pressure is defined as the amount of force per unit area. So if we imagine that we have two forces, one force is being applied to a very small area, the pressure that would result would be very high. If that same force is being pushed down on an area that's spread out much larger, the pressure would go down. Gases are always exerting pressures when the particles are colliding with the walls of the container. Anything that causes more gas particles to hit the walls will cause the pressure to increase, or if something causes the particles to hit the walls with a greater force, that will also cause the pressure to increase. We are most familiar with the pressure of the air around us, which is referred to as atmospheric pressure. The air around us is a mixture. It's primarily nitrogen, and the next is oxygen, and there's also some trace amounts of other gases such as noble gases within that mixture. The molecules in the air collide with any object the air contacts, and by doing so it produces a pressure. This pressure is the atmospheric pressure that we're all familiar with. We don't really feel it because we're used to it. A barometer is a device that is used to measure atmospheric pressure. We can look at a simple barometer on the right. The simplest type of barometer is called a Torricelli barometer. It consists of a glass tube that's sealed at one end. The height of the column could be 80 centimeters or more in length. The tube is filled with mercury and capped and then inverted. Its capped end is immersed in a dish of mercury. When the cap is removed, some of the mercury will run out, but not all of it. This is because the atmospheric pressure is pushing on the surface of the mercury inside of the dish. So those red lines are representing the atmospheric pressure pushing down that's all around us every day. Opposing the atmosphere is the downward pressure caused by the weight of the mercury that's inside of the tube. When the two pressures are equal, no more mercury can run out, but a space inside of the tube above the mercury level will have been created, essentially having no atmosphere, or we would say there's a vacuum at the top. The height of the mercury column that would be measured from the surface of the mercury in the dish to the top of the mercury within that column is directly proportional to the atmospheric pressure. And in our diagram, that would be that 760 millimeters. That's the height of the column when the atmospheric pressure is pushing down on the dish of mercury. Most people live in an area where the height of this column will fluctuate between 730 and 760 millimeters of mercury, which will use the symbol mmHg. This is often used as a unit of pressure, even though we're just reading the height of the column because it corresponds to an atmospheric pressure. The height of the column will tell us specifically what that atmospheric pressure is for the day. So this is a device that's often used by meteorologists. There are many different units of pressure. You're going to want to be familiar with these units and be able to interconvert between them if you are given the conversion factors. The SI unit for pressure is the Pascal. The Pascal is abbreviated with capital P, lowercase a, and it's defined as the force per area. Force is measured in units of newtons, which is what the capital N represents, per meter squared. Meter squared would be our area. Pascals are not used too much in a lot of our gas problems. Instead, we use a unit known as atmospheres. Atmospheres are abbreviated with the symbol ATM. 1 atmosphere is equal to 101,325 pascals. So you can see that the pascal is actually a rather small unit of pressure. Another pressure unit you might have heard about on the weather would be a millibar, and that's just part of the bar. 1 bar is equal to 100 kilopascals. Torrs are another unit of pressure, and 1 ATM equals 760 torr, which is also equivalent to the last unit of pressure, millimeters of mercury, abbreviated mmHg, which comes from the barometer that we saw on the previous slide. 1 torr is also equal to 1 millimeter of mercury. You may be familiar with units of millimeters of mercury if you've taken a blood pressure before. The systolic and diastolic pressures are measured in mmHg, usually on the blood pressure device. Another pressure unit that we use in the US often when we're talking about filling tires, for example, is PSI, which stands for pounds per square inch. So pounds would be representing the force being applied, and then it's per square inch because inches is what we use commonly instead of meters squared. So there are many other units of pressure out there, but the ones listed here are going to be the ones that we primarily will use within this chapter. Many different gases will have different chemical properties, even though they could be very different in terms of the way that they react. They all have similar physical properties that they obey, just because they are a gas. So it doesn't matter if we're talking about carbon monoxide, nitrogen, hydrogen, helium, etc. Just because they are a gas, they are going to follow the same set of physical properties. So we'll look at what some of these properties are. For example, we'll talk about pressure, volume, temperature, and the amount of moles of gas. In this section, we will study situations in which the amount of gas measured either by moles or grams would remain constant, and then we'll observe how the gas samples respond to changes in pressure, volume, and temperature when we fix another one of those variables. The gas laws will summarize experimental observations that are seen when we alter some of those variables. The pressure and volume law, temperature and volume, pressure and temperature, and the combined gas law will be the 4 different gas laws that we look at individually. Before we actually dive into the numbers, let's see what these laws consist of. Our pressure volume law is also known as Boyle's law. We want to study pressure and volume, and we want to hold temperature constant and also the number of moles constant so we can see how pressure changes or volume changes. So imagine that we have 2 different cylinders, and we want to think about what the pressure inside of each cylinder will be. Pressure is going to come from those gas particles colliding with the walls of the container. The more collisions they have, the greater the pressure inside of the container will be. We have 14.7 psi as the pressure on the left, and that gas is occupying some volume. We can see it's at kind of a big volume. What's going to happen when we push down that imaginary piston on the top and we decrease the volume of the gas? So we still have the same number of moles contained within that space, but now we're pushing it down into a smaller volume. And you can see it goes up and up and up. It goes from 25 to 35 to 50 psi as the volume gets smaller and smaller and smaller. So we can see that compression of a gas increases the pressure inside of the container which it is confined to. Therefore, we would say that pressure is inversely proportional to volume. If you're in a large volume, you're going to have a smaller pressure. If your gas is in a smaller volume, the pressure is going to be greater. Hence, the two are inversely proportional to one another. We can write this mathematically by saying volume is inversely proportional to 1 over P. If we want to take the proportionality sign out and replace it with an equal sign, we would have to introduce a constant. The capital C is our constant. We're not really interested in what that constant is, but it would be dependent upon what the identity of the gas is. If we want to talk about an initial state and a final state and talk about two different volumes and two different pressures, first we could solve for that constant and we would have PV equal to C. And we could set two systems equal to each other because that constant would be the same. And that leads us to our first gas law. P1V1 is equal to P2V2. So we could think about P1 and V1 as being some initial state and P2V2 as being some final state. And if we know three of the variables, we could solve for the missing fourth variable. And remember, we're holding temperature constant throughout this, and we're holding the number of moles constant. So we're just looking at how pressure affects volume, or volume changes affect pressure. This is known as Boyle's law. The next gas law relationship we'll look at is the relationship between temperature and volume. In this case, we want to hold the pressure constant, and we're still always holding N, or the number of moles constant. Let's imagine we have an initial state and a final state of a gas. On the left-hand side, where we have a low temperature, which we're going to refer to as T1, we can see that our gas occupies some volume, which would be referred to as V1. The temperature is going to be reading the amount of kinetic energy of those gas particles, and the more or less kinetic energy that they have will cause fewer or more collisions when they hit the walls of the container. So imagine if we go to some final state, and now we're increasing the temperature. So T2 is greater than T1. We can see that just by looking at the size of the container, that V2 is greater than V1. So the volume of the gas greatly increased because it expanded when more kinetic energy was put into the sample through the increase in temperature that we measured. If we add kinetic energy to our gas sample, the particles are going to gain that kinetic energy, and then they'll begin hitting the walls of the container with a greater force and more often, therefore causing the pressure to go up. But since we're assuming we're at a fixed pressure, the volume would have to expand to alleviate some of that pressure that would be created. Hence, the volume will end up being greater. The volume, therefore, is directly proportional to temperature. So V is proportional to T. If the volume goes up, the temperature must have gone up. If the temperature goes down, the volume of the gas will go down. So this is assuming that we're holding pressure and number of moles constant. Just like before, let's get rid of our proportionality sign. In order to change that to an equal sign, we would introduce some constant that would be dependent upon the gas. And we want to talk about an initial state and a final state to see how things change. We can solve for our constant. That would give us V over T is equal to C. And we can set this equal to another state where we have volume and temperature. And that will lead us to Charles' law, or our second gas law. V1 over T1 is equal to V2 over T2, where V1 and T1 could represent our initial state, and V2, T2 could represent some final state. And since we're still talking about the same gas and the same number of moles, C essentially cancels out. It's important that when we are looking at gas laws that involve changes in temperature, that the temperature that we use and talk about is in units of Kelvin. Kelvin is referred to as the absolute temperature scale. Recall that the temperature in Kelvin can be calculated by taking the temperature in Celsius and adding 273.15 to it. If we were to look at temperatures and compare them with the volume of gas at that certain temperature and extrapolate all of them backwards, all of those gases will eventually reach zero volume at a specific temperature. That specific temperature is 0 Kelvin, or -273.15. This is referred to as absolute zero. Absolute zero is nature's coldest possible temperature. It's the temperature at which all molecular motion comes to a halt. So if there's no motion of those particles, they have no kinetic energy. And if there's no kinetic energy, there's essentially no collisions happening. And so therefore they would occupy zero space or have zero volume overall. It's important that when we are plugging into our gas laws that we have our temperature in Kelvin, because we cannot have negative volumes or negative pressures, as we'll see later too. And so if we are in the absolute temperature scale, the temperatures are always going to be positive if we are using the Kelvin scale. So you have to be sure to convert to Kelvin before you use Charles' law. Next, we'll study the relationship between the pressure of a gas and its temperature. So this means that we're going to be holding the volume of the container constant, as well as the number of moles will not change between our two states. If we look at the diagram, on the left-hand side, we have a gas that's at a low temperature. You can see that it's moving very slowly within its container, and the particles are not hitting the walls very often or with very much force. So the gas at a low temperature is also going to exert a very low pressure. Now imagine that we have a gas at a high temperature. Those particles have much more kinetic energy. They're hitting the walls of the container with more force and much more often. So that gas at a higher temperature is going to exert a higher pressure if it's being fixed within the same volume. So we can see that the temperature and the pressure are directly proportional to one another. Low temperature equates to low pressure. High temperature equates to high pressure. So to get rid of our proportionality constant, we'll introduce, or get rid of our proportionality sign, we'll introduce our gas constant. We'll solve for our gas constant, C. That would mean pressure over temperature is equal to C. And we want to talk about two states to compare, so some initial and some final state, which we often refer to by using subscripts 1 and 2. And so that would mean that if we bring in another gas that has the same constant, we can set those two equal to one another. So P1 over T1 will be equal to P2 over T2. And this is going to be our last gas law that we look at. Next, we'll try some examples where we actually solve for some of this data quantitatively. A balloon with a volume of 2 liters is filled with a gas at 3 atmospheres. If the pressure is reduced to 0.5 atmospheres without a change in temperature, what would be the volume of the balloon? So we looked at 3 different gas laws so far, and we want to think about what one we are actually going to need to use in order to solve the problem. Notice we are given volumes and we are given pressures. We're given one volume and we're given 2 different pressures. And so out of the gas laws that we talked about, this is going to be looking at the relationship between volume and pressure, also known as Boyle's law. Boyle's law is P1 V1 equals P2 V2. And so we want to figure out when we reduce the pressure from 3 atmospheres down to 0.5, what's going to be the change in the volume. And we'll start out when we're studying gas laws by making a chart that talks about the initial and the final state of our gases, pressure and volume, and then how they change to think about what our final answer should be before we do any work. So in this one, we're looking at specifically pressure and volume. So those will be the 2 things. And our initial pressure was 3 atmospheres. Our final pressure is reduced down to 0.5 atmospheres. Our initial volume is 2 liters, and we don't know what our final volume is. In terms of the units for pressure and volume, we can plug in any units that we want. Whatever we plug in for the V1 and P1 will be what we get out for P2 and V2. We just have to make sure that our units match. So in this case, our final volume when we get our answer will be in units of liters because our initial volume was in units of liters. We are decreasing the pressure, so that's going down. We talked about that there is an inverse relationship between pressure and volume of a gas. So if our pressure is being reduced, we should expect our final volume to be greater than 2. So let's use Boyle's law and rearrange and solve for V2. V2, or our final volume, will be equal to P1 times V1 over P2. And then next we're going to plug in from our chart. P1 is equal to 3 atmospheres. V1 is equal to 2 liters. P2 is equal to 0.5 atmospheres. And you can see why the units don't particularly matter as long as they're the same. Units of atmospheres will cancel, and we'll be left with units for a volume, which is what we're solving for, and they'll be in liters. And so we're going to end up having 3 times 2, or 6, divided by 0.5, which should give us V2 of 12 liters. And so just as we expected from our chart, our volume did increase because those two are inversely proportional to one another. A 600 milliliter sample of nitrogen gas is heated from 27 degrees Celsius to 77 degrees Celsius at constant pressure. What will be the final volume? So first we want to think about which gas law formula we're going to apply here. We're given a volume, and we know 2 different temperatures, and we're being asked for what the volume is. We're also told that the pressure is being fixed and held constant. So this is going to be our relationship between volume and temperature. Our formula is going to be V1 over T1 equals V2 over T2. We can also fill out our chart. So initial, final, and the change. And then the variables that we're looking at in this case are going to be the volume and the temperature, but we also have to be sure to convert our temperature, which is given to us in degrees Celsius, into units of Kelvin. So let's list temperature twice here. So starting out, we want to plug in what we know, and we know that our initial volume is 600 milliliters. We're trying to figure out what our final volume is. When we get it, it'll be in units of milliliters as well. Our temperatures initially in degrees Celsius is 27 degrees C, and finally it was raised to 77 degrees Celsius. And recall that your conversion is your temperature in Kelvin will be equal to your temperature in degrees Celsius plus 273. So if we add 273 to each of those, we'll get 300 Kelvin for our 27 degrees Celsius, and we'll get 350 Kelvin for our 77 degrees Celsius. So our temperature, the change is, it's going up, it's increasing. And recall, when you are measuring temperature, you're measuring how much kinetic energy something has. And so if those particles have greater kinetic energy, they're going to be moving around faster. And if the pressure is fixed, the volume must expand. So those two things are directly proportional to one another. So if temperature goes up, volume must also go up. So we should expect a volume greater than 600 milliliters. All right, let's rearrange our formula for V2, or V final, which is what we're solving for. So first we can cross multiply. That would give us V1 times T2 equals V2 times T1, and V2 will be equal to V1 times T2 divided by T1. Next, we want to plug in everything from our chart. So our chart really just helps keep us organized to make sure that we're putting the correct volumes and temperatures into the initial and final spots. So initially our volume was 600 milliliters. T2, that's our final temperature, that was 350 Kelvin, divided by T1, which is 300 Kelvin, our initial temperature. You can see that units of Kelvin will cancel, and our milliliters are on the top, so that'll be our units for V2. So our final answer here should be 7 700 milliliters. And just as we expected, we got a greater volume because we increased the temperature, and volume is directly proportional to temperature. The three gas laws we've just examined can be brought together in one single equation. This is known as the combined gas law. It says that P1 times V1 over T1 equals P2 times V2 over T2. The only requirement is that our temperature is in units of Kelvin, just as we saw with the other gas laws. Pressure could be in any of those units we talked about, atmospheres, torr, pascals, as long as it's the same on the left-hand side and the right-hand side. Volume could also be, for example, in units of milliliters or liters, or technically even centimeters cubed, as long as it matches. The only requirement is that we're using the absolute temperature scale of Kelvin so that it's always a positive temperature that we're plugging in. Usually we use the combined gas law in problems where we know some given set of conditions of temperature, pressure, and volume. And we wish to find out how one of these variables will change when the others are changed. So now we're not just required that we can adjust one variable at a time. Maybe we change pressure and volume and we see how temperature reacts. Maybe we change volume and temperature and we see how pressure reacts. That would be an example where we want to use the combined gas law and not one of the individual gas laws. A 275 milliliter gas sample is initially at 22 degrees Celsius and 5 atmospheres of pressure. What is the final volume when the temperature is changed to 30 degrees Celsius and the pressure is changed to 2 atmospheres? So let's make our graph. We have our initial, our final, and then our change. And our variables that we're going to be looking at in this case are going to be our pressure, our volume. We can make a list of our temperature in degrees Celsius and our temperature in units of Kelvin. And really this is just so you can keep track of everything before we plug it into the combined gas law. And so we have our pressure initially at 5 atm. We were told the final pressure will be changed down to 2 atmospheres, so that's decreasing. Our volume of our gas initially occupies 275 milliliters. We're trying to figure out what that final volume is. That's what we'll be solving for. And based upon Boyle's law, the pressure is decreasing, so we should expect volume to go up, but we're not sure if temperature is going to be opposing that or not yet. Our initial temperature is 22 degrees Celsius. Our final temperature is 30 degrees Celsius. And so we're going to add 273 to each of those to get our final temperature and our initial temperature in Kelvin. So 22 plus 273 will be 295 Kelvin. And 30 plus 273 will give us 303 Kelvin. So our temperature is increasing and our pressure is decreasing. Temperature and volume are directly proportional to one another. So since temperature goes up, volume should go up. And pressure is inversely proportional to volume. So since pressure is going down, volume should also go up. So the pressure and the temperature are not opposing one another in what happens to the volume of the gas. So for sure, we should expect our volume to increase. Our combined gas law, P1 V1 over T1 equals P2 V2 over T2. We can first cross multiply, and that will give us P1 V1 times T2 equals P2 V2 times T1. And in this case, we're solving for our volume, our final volume, what we're referring to as V2. So V2 will equal P1 V1 times T2 divided by P2 times T1. So you can already see that the pressure and the temperature are going to end up canceling. So let's plug in our units from our graph here, our values. Pressure 1 is 5 atmospheres. Volume 1 is 275 milliliters. Temperature 2 in Kelvin, 303 Kelvin, divided by pressure 2, which is 2 atm, times temperature 1 in Kelvin, 295 Kelvin. So our atmospheres will cancel, our Kelvin will cancel. We'll be left in milliliters, and our V2 that we should get should be greater than V1 because our volume should increase. And the answer is 706 milliliters for our V2. Combined gas law, you're going to notice that you're given a lot more variables that you have to plug in when you have more changes happening than just one. So it's going to be slightly obvious when you need to use the combined gas law.